Hello, this is Ghazal. I'm a second year PhD student of industrial engineering. I'm working on modeling microgrid systems. A microgrid is a local energy grid with control capability, which means it can disconnect from the traditional grid and operate autonomously. The grid connects home, businesses, and other buildings to central power sources. But this means that when part of the grid needs to be repaired, everyone is affected. There is a where microgrid can help. A microgrid generally operates while connected to the grid, but importantly, it can break up and operate on its own using local energy generation. Microgrid can be powered by distributed generators, batteries, and or renewable resources like solar panels and wind power. But the amount of wind power and solar energy is uncertain, and we should generate some probabilistic scenarios for them by using some scenario generation methods. Probabilistic wind power scenarios constitute a crucial input for a stochastic day-ahead unit commitment or microgrid systems. To minimize the cost, uh, if the generated set of scenarios will represent the joint distribution of the uncertain parameters, I mean solar energy amounts or wind power amounts, then a good solution for this that would be obtained. We call these scenarios as reliable scenarios. Uh, Sometimes we can solve the problem, I mean the optimization problem, to obtain the optimal value of cost uh, by solving the problem every time using every scenario and compare them with the optimal value of the problem obtained by considering the observations. And we can find the reliable scenario, but it's a very time consuming process. So we should find a way to find reliable scenarios. And the question is that how we can determine that how well those scenarios represent the true distribution of the observed data. This is where I came in, and my qual paper was about assessing the reliability of scenarios. I found a way to assess the reliability of scenarios, and now I'm working on modeling of energy management systems, I mean microgrid. And after finding a suitable model, I used that scenario reliability method to use some reliable scenarios for my model to find the minimum cost for a microgrid. This is what I have done so far, and what I'm going to do in the future. I hope I can do my best.
Use of fertilizers containing high amounts of nitrogen has been crucial in helping farmers increase corn yields and meet the needs of an ever-growing population. Unfortunately, not all of the nitrogen in those fertilizers ever meets its intended target. In order for corn to have its nutrient needs met throughout the growing season, farmers will apply fertilizer early on, long before the crop has a high need for nitrogen. During this lag between application and plant uptake, the nitrogen in those fertilizers is left vulnerable to environmental losses, such as nitrate leaching and nitrous oxide emissions, each with their unique consequences. Nitrogen in leached water can be carcinogenic and can contribute to the degradation of an ecosystem downstream from a given field. Alternatively, when loses nitrous oxide, the nitrogen from those fertilizers gets transformed into a greenhouse gas, 300 times more potent than carbon dioxide, and with the additional capacity to contribute to ozone destruction. Given these problems and the need for fertilizer, it is imperative to properly understand how much nitrogen from fertilizer succumbs to these environmental losses. In the past, many studies have used traditional field plots to do this, However, there's a problem with using such plots to study nitrogen loss. Traditional field plots are open both on the sides and on the bottom to the surrounding soil, so any water entering the plot can freely escape through these open sides and bottom, taking with it nitrogen we are trying to track. When this happens in our studies, the fertilizer that we apply ends up getting diluted into the surrounding soil, making it difficult to measure its contributions to environmental losses. This is where my research comes in. For my PhD project, I'm using a novel field design you can see in the picture. My research addresses the problems of traditional field plots by harvesting massive blocks of soil and fully enclosing them both on the sides and on the bottom with steel, as you can see in the diagram. To the bottom of every soil block is a single pipe that collects all of the excess water that would normally be lost through the sides and the bottom. By fully enclosing the soil with steel and completely collecting all of this water, I am ensuring that there'll be no sneaky escapes for nitrogen diluting my fertilizer applications. Into every block then, I'm applying a given fertilizer rate that I'm interested in studying and growing corn just as you would any traditional field corn. Except, of course, I'm also taking numerous measurements of nitrate losses and nitrous oxide emissions individually from each block. With these measurements, I'll be able to better understand how much nitrogen in fertilizer succumbs to environmental losses affecting both our own health and our planet's health. Thank you.
Hello everyone, my name is Jarrett Morrison. I am a master's student here at Iowa State in the Department of Civil, Construction, and Environmental Engineering. I'm working with Dr. Lu Liu here on campus, and today I'm going to talk a little bit about our research of enhancing the resilience of Houston's wastewater system under wet weather using emerging technologies. So the study area that we will be looking at is the Houston, Texas area. And in 2017, we observed a hurricane that devastated much of Texas, and specifically the Houston area. As a part of that, we observed many of the wastewater treatment facilities flooding, and as such, they were failing in their conditions and not able to meet our regular standards. And so that's part of the project here, is to use emerging technologies to, one, model what was going on in this flooding event, but also to see if we can enhance the resilience of these emerging technologies. So our objectives are quite simple. Well, we were working with Howard and Rice University on this project, where we used membrane biofilm reactors in order to, one, observe how those emerging technologies can affect a wastewater treatment plant, and also to observe how that looks under wet weather conditions. Our goal in this part of the project, Dr. Lu Liu and I are working on creating a whole system level where we're modeling the entire wastewater system of Houston, Texas, and using those emerging technologies, biofilm reactors, in order to improve the resilience. That is the goal of what we're trying to do. So overall, what we are expecting to see is a performance curve similar to this, where we have our constituents such as nitrates that we naturally have removed in our wastewater treatment plants. And we'll see that under wet weather conditions, when they were failing, a lot of these wastewater treatment plants were not meeting the appropriate amount of removal. And so we see this dip in removal rates, and then it slowly returns back to normal. What we want to see with implementing these emerging technologies is that we decrease the amount of reduction, decrease that level of dip, and also improve our recovery time. So that way we can measure the resilience of using emerging technologies in this case.
Hypoxia zones are regions with reduced level of oxygen in the water. They are also called dead zones because marine life either lives or dies, and thus those regions becomes biological deserts. So those zones are caused due to nutrient pollution. Excess nutrients that run off from agricultural land can be one of the stimulators of an overgrowth of algae, which then sinks and decomposes in the water. This process consumes oxygen and depletes the supply available to healthy marine life. Therefore, understanding Iowa's role in nutrient pollution is a great deal to help with the control of hypoxia zones in the U.S. Iowa has also a huge impact as an agricultural producer, being responsible for food, feed, and energy production. It is already proved the contribution of fertilizer use to nutrient pollution, but because production maximization is a worry, quitting the use of fertilizer is not an option. Therefore, in my research, I expand the IFUS, Iowa Food, Energy, and Water Nexus model to better understand the direct relationships between nitrogen runoff, food, feed, and energy. With mass and energy flow, it is possible to model those relationships, how nitrogen input, for example, commercial fertilizer or manure, is involved in the production of food, feed, and energy products. With defined relationships, I understand better cyclical IFUS relationships. Finally, I simulate different scenarios with the IFUS variables. For example, I can use conservation practices as crop rotation to better manage nutrient availability and thus minimize commercial fertilizer usage. At the end, I am developing a visualization tool that enables understanding of the relationships between food, feed, biofuels, and nitrogen export as a proxy indicator of water quality. This tool facilitates decision-making, maximizing agricultural production while respecting nutrient management practices.
Hello everyone, my name is Kelly Nascimento Thompson. I am a second-year PhD student in the Department of Agriculture and Biosystems Engineering under the supervision of Dr. Brian Gelder and Dr. Richard Cruz. The title of my dissertation is WEP DEP Model Parameterization for Evaluating Placement of Prairie Strips Across a Range of Hill Slopes and Soil Types. My research interests involve geographic information systems, remote sensing, and programming. For GIS, we will understand where, why, and how patterns happen with spatial data. And with remote sensing, we can collect information at a distance based on reflected or emitted radiation from the targets. And programming will help us automate data processing, visualization, and analysis. So discussing how to implement the DEP project within the STRIPS project, we want to use the strip sites and the strip prairie as a management input within the WEP model. Here, we have a picture that represents what the WEP model looks like on the Windows interface. And it requires inputs like management, slope, and soil. And this is what a hill slope looks like. And management, slope, and soil combined represent an overland flow element, OFEs. So our main goal is to work on the management side of things. We want to implement the prairie as a management file in the WEP model so we can compare our estimations of runoff and sediment to those obtained at the field level collected at the H-flumes. This image represents a strip site, right? And we have the two paired watershed sites. So control means no prairie, right? Just conventional corn or soybean being planted. And then the prairie has the prairie strips planted in several sections of the field. And these small dots that we see on the figure represents the flow paths. The flow paths are generated by the WEP model, and that's where the water is flowing towards the lowest point of the watershed where the H-flumes are located. The STRIPS project is divided in two phases, And the phase 1, which started in 2007, was implemented at the Neil Smith National Wildlife Refuge. So in 2020, Dr. Brian and I and other students, we went to this site to check out what the H-foam looks like. So that's where all the sediment and runoff comes down to at the end of the watershed. This research is ongoing and some changes might still happen. I appreciate your time. Thank you.